So, yeah, there's a problem. I know I mentioned it at various points in my videos, but I didn't make as big a deal of it as I probably should have. So on Ren's website, with the mineral weathering in Scotland project, they claim that the carbon that is sequestered in the production of calcium carbonate is permanent in rock. There's a very basic problem with this, and that is that calcium carbonate is a salt, which means this calcium is an ion, and this CO3 over here is an ion, and this is an ionic bond that they share. It is not covalent like these oxygens to this carbon. It is ionic, which is why which is why tap water, groundwater, well water is pretty much always hard water, because that water in the ground is in contact with some amount of calcium bearing minerals, and the most abundant of those is calcium carbonate. And what the water does is it just kind of says, hey, you know what? No, I want to take this calcium with me. Because water is a polar molecule. So it is charged. It is electrically charged. It acts like it's ionized, even when it isn't. So ions dissolve. Or they're like... salts like this tend to dissolve in water. That's what I want to say. Salts tend to dissolve in water because the water fucks with this ionic bond. So what happens in water when you put sodium carbonate in water? Some of it will actually dissolve. Right? And in doing this, you're actually going to produce some CO2. Because what's going to happen is you're going to get two of these guys. Or, I don't know, some number of these guys, and the oxygens are going to do some, and you're going to get CO2s off of it. And the calcium's going to sit there in the water. And then what happens when you get, when you dry out the water, you dry out the pan or whatever, and you get that lime scale. Those calcium ions that were in the water can't evaporate off like the water does, so they stay behind. And guess what's in the air? CO2, so it's going to recombine with the calcium and make fucking limescale. And some of these will also just be like sitting around too, like they're not all going to go away. Some of these are going to sit there too and just kind of recombine as the water disappears that's fucking with their bonds. But this is not by any means a permanent mineral. This is not a permanent rock, right? Simple contact with water totally jacks up this material, just like it does with salt, right? So like you stir a little bit of salt into water and it just seems to disappear, right? It's because sodium chloride is like this. It's an ionic bond. The material doesn't actually even exist anymore in the water. There is no sodium chloride unless it's oversaturated. If it's oversaturated, then the water can't take anymore, and you're going to get like a pile of it at the bottom that is actually structurally sodium chloride. But the sodium and chloride ions in the water are not forming ionic compounds. in the water. They are dissociated from each other. And then that's the same thing that happens here. And all it takes is water. So, why my rainwater filtration system, the water that I get out, I put it through the filter just to make sure that it's clean of, disease and parasites and whatever. It goes through sand and then a whole bunch of charcoal. And at the end of it, it's actually harder because it's going through that sand. Because of this exact process. What it's doing, mostly it's pulling calcium ions, some magnesium as well. But if you measure its hardness, it's way softer than my tap water. Way, way, way softer. But it is harder than rainwater, right? If you measure the hardness of the rainwater that I'm sourcing, you measure the hardness of my filtered rainwater, they're different from each other. The rainwater is softer than my filtered rainwater, and they're both significantly softer than my tap water. But the reason that the tap water and the filtered rainwater have hardness at all is because of this, is because calcium carbonate is a salt of calcium. So this is by no means a permanent rock. This is very susceptible to change, to dissolving, to becoming dissociated, and then this component fucks off and turns back into CO2. Is very, very highly subject to that. Mere exposure to an acid will cause it to do this. So if your pH is down just a little bit below 7, it's going to start doing this. So that claim right there on the face of it is just not true. What they're saying there, that it's permanently trapped in the rock, that is not true at all, because this is a salt. And one thing that will happen if you've ever kept mollusks, you don't want to use soft water. You don't want to use like distilled water or rainwater really with them, because it's so poor in calcium ions. It will actually dissolve their shells. The water will actually, on this living organism, that is, it will break down their shell while they're alive. Or, if you're more fortunate, it will just stunt the growth of their shells. Yeah. So this is a very real thing. This is a problem. This on its own is not enough to really ensure that your CO2 that your carbon is actually sequestered relatively permanently. Because what will happen is, as the rainwater percolates through the soil, it will dissolve your calcite, your limestone, your whatever, aragonite I think is one of them. There's a whole bunch of different names for this material. It will dissolve it. And that's actually how you get formations like stalactites and stalagmites in caves. It's primarily this material being deposited, being moved around, shuffled around in the ground by water. That's how easy it is. And it makes sense, because recall how easy it is for this to form in the first place. All that basically has to happen is you get contact between this material that has calcium in it and the air. We don't have to apply special temperatures, special pressures. We don't have to have like some special catalyst to cause this. It just happens naturally. Pretty like what? This is a reaction that wants to happen, but it happens so easily that of course it's a weak reaction. Of course this is not a covalent bond between them. Something like nitrogen fixation takes way more effort because it's a covalent bond. or it's multiple covalent bonds, and you're having to break, what, 3 covalent bonds between your 2 nitrogen atoms in your N2, and then what, put hydrogens on it, so you get ammonia, something like that. Yeah, this is by no means a permanent thing here. Yeah, I thought that was worth pointing out.